What I'm going to do today is discuss near eye versus far eye AR projection. Now, a lot of people have heard about near eye projection because that's the most common one, where your eye is looking at a screen that's transparent and they're looking at some real world object, so in this case a tree. So what happens is the screen could render a person on the digital screen, and because it's transparent you can also see the tree at the same time. So you get this AR experience where the tree looks like there's a man in front of it. Now this all works in theory except for one small problem, and that is unfortunately field of view. And to understand this, I will just do what this screen would look like. So what you'd expect is that person takes up the full screen, because as a human you've got quite a large range of field of view. But even on a pair of glasses, this isn't actually the case. So what happens is the digital screen only fills part of the area up. So in our example here, the human will lose his head and he'll lose his legs. So it crops quite significantly the picture. And this is why we have these weird sort of conversations where you don't get shown the actual image of what it looks like behind the lens for things like Magic Leap or HoloLens, because you get this effect of everything being cropped. So what they show you is these CGI images where they'll be put back in to make you say, oh, well, that's what it's going to look like in the future. So what I'm going to do now is show you how far eye renders it and how it doesn't have this issue. Far eye AR projection works slightly differently. You need a board to look at, similar like a cinema screen. Now, the eye is now looking at the board, and instead of being several meters away, it's only sort of 3 or 4 feet. And this is the line of sight going down to the board. Now, what's being clever is the image is being rendered here, not being rendered here. And the way it does that is you still wear glasses and they're at a slight angle. Now, what happens is the projection goes to the glasses, but then it follows the line of sight down. And because the material on the board is special, it then rebounds at exactly the counter angle to the eye. Now, this has an advantage with field of view. And if we go back to our man problem previously, we can see what's going on. So before, we had the lens and you had the person that you were hoping to see. Now, with far eye AR projection, you have the ability to overscan rather than underscan, which means your eyes will see a much larger field of view, which means that when we get a camera and we look at a man, or in this case a big purple alien, through the camera, then what you'll see is that 3D image, and we're going to do that now. So I'm going to pick up the camera and we're going to look at the AR glasses, and most important bit is look through the lenses. Now if we do that, you will see that at the bottom of the screen you can still see stuff even though they're not by the lenses, and there's slightly different images in each lens because the light is polarized and the lens is at a different angle, so that's why you can see 2 whoops there. But obviously when you start looking through the lens you can only see one of them. So that's how it gets the 3D image. In addition to that, we can have a quick look at the glasses and we can see that they're at a slight angle, and if we go right underneath we can see the projectors. But there's all sorts of other clever stuff going on here, and we'll discuss that. The board has an interesting property. Now, as we discussed, when you're looking at it, the light returns exactly back along the line of sight, but it really shouldn't do that. It should disappear off in the opposite direction. So what's happening there? To understand that, you have to look very closely at the board itself. The board is actually made up of tiny little balls. And what happens is, when the light shines down, and I'd make a bigger ball, it's actually hitting the ball perpendicular, which means it's responding in exactly the same direction. So the board isn't actually flat, it's actually made up of lots of little balls. Now, what's also really clever about the board is this material is actually quite common garden stuff. This is what you find in reflective jackets and other types of material. So what we've got here is just a large sheet of it. Now, those of you who were looking carefully will have gone, well, I saw you looking through the glasses and the whiteboard wasn't working. So what was that? You said it filled the whole lens glass. Well, let's move the camera again, and I pick it up, and you've seen me look at that, and I go there again. Here is the material, and as you see, it quite happily covers that all up. So if I move that again, that's what's happening. So that's one thing that's really cool, is the board itself has a material property that reflects light back in the same direction. And as I said, what's extra clever about that is that standard reflective material. That's nothing special. You can buy that by the yard. It allows you to have a screen that is suddenly flexible, which has all sorts of properties in itself. Finally, you have the controllers. Now, the exciting thing about that is, if you think about it, your mouse can only go in two directions. Whereas this wand can go equally in two directions, but it can also go in a third. So let's think about that. That means you can manipulate a 3D object in a 3D space. Remembering also that the mouse is talking to a 2D screen, whereas this wand is talking to a 3D environment. And that opens up all sorts of potentials, not only from a gaming point of view, but also potentially from a data and financial one as well.